Think of opposite of derivative. Derivative of this is this. So the antiderivative of fx small would be this capital Fx. So this is antiderivative type of definition or understanding it as an inverse process of differentiation. But in this inverse process, there is a slight problem, because ddx of fx plus some constant would also be the same small f of x, because ddx of c is 0. Then it means that integral of fx dx can also be fx plus this c, where c is entirely your choice. If c is entirely your choice, then we call it arbitrary constant. It doesn't have to have a fixed value like Planck constant has. C equal to 1 is also happy, C equal to 2 is also fine, 100 is also fine. It is arbitrary constant. So generally speaking, antiderivative of fx is this fx plus any arbitrary constant of your choice. It is not unique. It is not only this. It is not unique. If you get some function plus some arbitrary constant, what does it mean graphically? If you get some function plus arbitrary constant, say for example, you have a function like this, right? Call this as maybe y equal to x by, let's make it simple, y equal to x. Y equal to x. So if I add some number to the right side, x plus 1 or x plus 2, it means I'm increasing the height of y. X plus 1. I'm not changing the slope. Slope is the same, 1. It is the height at which it cuts y-axis. 0 unit, 1 unit, 2 units. So just see what happens when you add some arbitrary constant. That arbitrary constant can be positive, it can be negative. It goes on and on and on. You get a family of curves. So antiderivative of a function is family of curves, unless you uniquely define arbitrary constant, make it a constant rather than arbitrary constant. Then it becomes a specific member of the family. Else it is the family. So that's the geometrical understanding of indefinite integral. It is not definite. It has arbitrary constant. It is not definite. Because of this antiderivative approach, getting several results as standard formulae is very easy. You know several formulae for differentiation, and just oppose it. ddx of sin x is cos x. That means integral of cos x is sin x. Make sure to add some arbitrary constant. So several formulae you can get from differentiation. Okay. Now, let's prove this formula. Now, by the way, integral representation must have this symbol along with this. This dx shows with whose respect are you integrating. I can integrate something with respect to x. I can integrate something with respect to x square, with respect to some special function. So this whole thing, 1 and this, that whole thing combined is a symbol for integration. It's an operator. Proof is very simple. Differentiate the right side. That's it. Consider RHS. Consider the derivative of RHS. And you will have no problem in getting x to the power n. Just do it. If you have any problem, let me know. You can raise your hand if you have any problem. When n is -1, then the situation is different. Integral of x to the power -1 or 1 upon x is log x, mod x, log of mod x. Now that's also very easy to prove. We will consider RHS. Two cases as usual to get rid of mod. For this case, differentiate and you will get 1 upon x. For this case, you have log of -x plus c. Differentiate this also and you will get 1 upon x. If you have any problem, raise your hand. I suppose there are no questions. So making use of this antiderivative approach, we can get several results. ddx of e to the power x is e to the power x. So integral of e to the power x will be e to the power x plus c. ddx of sin x is cos x. So integral of cos x would be sin x plus c. How about this? Integral of sin x. The answer is minus cos x. Proof is very simple. Just differentiate the right side and see if you get sin x or you don't. You will get that very easily. ddx of tan x is sec square x. So integral of sec square x will be tan x plus c. ddx of cot x is cosec ddx of cot x is minus cosec square x. So integral of cosec square x would be minus cot x plus c. Then ddx of sec x is sec x tan x. So integral of sec x tan x would be sec x plus c. Then d dx of cosec x is minus cot x cosec x. So integral of cosec x cot x would be minus cosec x plus c. Then d dx of sin inverse x is 1 upon root 1 minus x square. That means integral of 1 upon root 1 minus x square would be sin inverse x plus c. d dx of tan inverse x is 1 upon 1 plus x square. So this would be tan inverse x plus c. d dx of sec inverse x is 1 upon x under root x square minus 1. So this fellow would be this. Very simple to get all these results from inverse of differentiation approach. Any questions up to this point? Let me know. We now have a theorem . Let's prove it. Let integral fx be some function that function may have arbitrary constant inside it. So don't bother about arbitrary constant. So from the definition, this should be valid, but fx is this. And therefore, we have this. Any questions? Let me know. Alright. Next theorem. Constant comes out of integral. Proof. Consider this integral fx dx. Let it be f of x. Don't worry about arbitrary constants. You can imagine that it is built in. It is inside capital F. We know from differentiation okay, let me write one more step first. So from the definition, d dx of fx is this fx. We know from differentiation that if you differentiate something like this, then constant would come out. Right? This we already know. But ddx of this fx is this fx. Derivative of this fellow is this. From the definition, we have this, but fx is this thing. Integral fx dx. So that's proved. If there is any question, let me know. Alright. Here comes the next theorem. Integral of sum of functions. In fact, sum or minus. If you do, then it splits like this. It splits like this. Whether it will take 2, 3, 400, plus or minus, doesn't matter. Splitting will always work. So we can prove for this case, plus case, two of them. Likewise, it can be done for minus case, and likewise it can be done for as many functions as you wish, f1, f2, f3, f4, and so on. Let this fellow and that fellow also. This fellow be something, maybe capital F1. Again, don't bother about arbitrary constant. You can take it to be inside F1 and let this be this. So from the definition, we have F1 x as this, and from definition f2x equal to this, right? Now, we know from differentiation that if we have two functions or more, whether plus or minus, then splitting can be done like this. Okay? But ddx of f1 is this f1, and ddx of f2 is this f2, and now from the definition of integration, we have f1x plus f2x equal to integral f1x plus f2x dx, and capital F1x is this fellow, and capital F2x is this fellow. So let's put these at appropriate places. So we get integral f1x dx plus integral f2x dx equal to integral this plus this dx. So if you have any questions, let me know. In generalized situation, it would be like this: integral of k1 f1 plus or minus k2 f2 plus or minus k3 f3. Of course, it's x everywhere. X here, x here, x here, and on and on and on. Constant comes out. Okay, we can do in stages. First, we apply this theorem, which is about splitting. On and on and on. And then we can take these constants out from another theorem that we have discussed. If you have any questions, let me know. Some simple problems for practice. Try this. Just see if you are getting it. If you have any questions, let me know. No questions, so I suppose it is done. Try this. The approach would be to expand the whole thing using a plus b whole cube formula. Expand the whole thing, and then the answer you should get is this. See if you are getting it. Any questions? If you have, then let me know. No questions? We move on. Let me know if there are any questions. The approach would be to multiply these three fellows and then integrate. Well, I don't see any questions, so I suppose no problem, and we move on. Let's make it a little harder now. Now, how will you do it? Think about it. You can raise your hand if you need a hint. The hint would be to divide numerator by x plus 2. Divide numerator by x plus 2. And that you can do by actual division or by non-actual division also. So forcefully let's write x plus 2 for the numerator. To get x cube we must have x square, and that will get us 2x square, but we want 4x square. So we add 2x square minus 3x minus 2. This is n numerator. Then I want x plus 2. So again forcing x plus 2. To get 2x square, writing 2x here. 2x square is done. But 2 into 2, 4x is coming. We want minus 3x. So 4x minus 7x will get us minus 3x, minus 2. And now further, forcing x plus 2 once again, x plus 2. So minus 7, and then we get minus 14, we want minus 2. That means plus 12. Now you can see that it should work. 12 is remainder. X plus 2, x square plus 2x minus 7 plus 12. So when you have this integral x plus 2, x square plus 2x minus 7 plus 12 whole divided by x plus 2, then x plus 2 will cancel, x square plus 2x minus 7 plus 12 upon x plus 2. So x cube by 3 minus 2x square by 2 minus 7x plus 12 is constant, dx by x plus 2. Any questions up to this point? Let me know. Now the tricky part is the right side integral, because we have not done method of substitution yet. Actually, it requires method of substitution. Right side part. But then, you know from differentiation that when you differentiate d dx of sine x, answer is cos x, and when you differentiate d dx of sine of x plus something, answer is cos x plus that thing. You are familiar with this type of pattern in differentiation. Adding something to variable does not create any trouble. Adding something to variable, some constant to variable, does not create any trouble. So from that understanding, you can possibly say that if d dx of log x is 1 upon x, then d dx of log of x plus 2 should be 1 upon x plus 2. So that way you can get the answer. But there is a systematic method to handle this type of situation, which is method of substitution. That we will discuss later. If you have any questions, let me know. The questions, moving on. Try this problem. Okay, if anybody needs hint, raise your hand. Hint is same as the previous one. You have to do the division. Maybe you can go for this approach also. Without doing actual division, forcefully introducing denominators into the system. A very effective approach generally. X square x to the power 4 minus x square alone is not there. So minus x square. Then copying that one cell. Then dividing by x square plus 1. Now after this, forcing once again x square plus 1, so minus 1. Minus 1 will get us minus x square minus 1. We don't want minus 1, we want plus 1. So plus 2 divided by x square plus 1. This should be good enough. Well, actually, I am writing the denominator also. So I should call this fx. Fx is the whole thing. Plus 2. So we have x square minus 1 plus 2 upon x square plus 1. Now this integral is quite easy. This will be tan inverse. Let me know if you have further questions. No questions, I suppose. Moving on. Try this. The answer I have is 10x minus x plus c. If anybody needs a hint, raise your hand. The hint is tan square x is equal to x square x minus 1. Try to do further on your own. If you need further solution, raise your hand again. I suppose we can move on. Try this. The answer I have is x by 2 minus sin x by 2 plus c. If anybody needs a hint, raise your hand. Alright, the hint is to use the trigonometric formula. That's it. There's a private message. Oh yes, yes. Yes. Any other question or clarification? All right. There is no assignment for today. We stop at this point.